Hi, welcome to Physics 2211 Lab 2 on motion of a falling object. My name is Maria Jyotish, and let's get started. The purpose of this lab was to observe the motion of some object dropped from rest and falling somewhat slowly, and then to construct two computational models based on physics principles which we can compare our observed data to. Some fundamental physics principles and models we can see in this lab are Newton's second law, the momentum principle, which relates the net interaction between the system and its surroundings to the observed motion. We also see in our observational model that the net force, sum of all forces, may be impacted by the presence of gravity, drag, and other forces, whereas in our computational models we'll see how position gets impacted by the force of gravity with and without the force of drag. And for a brief preview, the three models, observed, computational with gravity force, and computational with gravity and drag force, show the impact of drag force causing the discrepancy between their data. As stated earlier, the purpose of this lab is to observe the position of an object at rest, falling, and then to analyze the impact of certain forces during the fall. Since our lab isn't in an ideal world, you'll notice that our observed data's net force will be impacted by gravity, the drag force, and other unknown forces as Newton's second law suggests. Our computational model, however, strictly only applies either just the gravity force or both the gravity and drag force to the net force. The position and velocity update formulas are used to create our computational models. Here is a video of our observed object, the system being the shuttlecock and the surroundings being everything else. I used Tracker to analyze the motion of our shuttlecock, and as you can see in this y-position graph, the trend of the position is the downwards nonlinear slope. Therefore, the velocity of our position graph is negative and not constant as the shuttlecock is traveling below the x-axis. Next, I used GoScript to create a computational model of an object falling with the force of gravity. First, you can see I changed the ball mass to closely match the average mass of a shuttlecock. Next, I updated the ball's initial position to match the initial position of the shuttlecock in the observational data. Then, I updated the delta t to match the frames of our video. Now, down here in our loop, you can see that our net force is calculated using only the force of gravity. Also, as mentioned before, our position update formula and velocity update formula are used to plot each data point as time passes in delta t increments. For my second computational model, I simply added the drag force to the formulation of the net force. B, the proportionality constant, was estimated using the computational model without gravity and experimental model. Then down here is the formula to calculate drag force. And now our net force is calculated with both the drag and gravity force. Once again, the position update formula and velocity update formula are used to plot each data point as time passes in delta t increments. Next, taking the observational and computational models data, I used Excel to create a position versus time graph to compare the results. You can see here that initially all the data sets aligned, but then later began to diverge. The observational and computational model with both drag and gravity force align the most. This is due to the computational model with just gravity force not accounting for drag, which would slow down how fast an object falls. That is why you can see here the object with no drag force is covering a larger distance. The discrepancy between the observational model and computational model with both drag and gravity force is probably due to human error of not plotting the points accurately in Tracker or due to other unknown external forces acting on the object in the observational model. Some follow-up questions are: examine the velocity versus time graph of models created and determine which, if any, model predict terminal velocity. Terminal velocity happens when the force of drag pointing up is balanced by the force of gravity pointing down. This would mean that the net force would be zero and therefore the object would be moving at constant velocity. You can see this is demonstrated by our second computational model, as it is the only one where the position is impacted by the drag and gravity force. And in our position graph here, you can see that the line becomes linear, implying the object is at terminal velocity. Now, what if the object was thrown downward, and how would the terminal velocity be impacted by this? There would be no impact on the terminal velocity, as the initial force is no longer acting on the object as it is falling in the air. Therefore, the net force is still only impacted by the drag and gravity force. The only thing that would change is the initial velocity, which doesn't determine terminal velocity. That concludes my Lab 2 results, and thank you for watching.